All right. So I guess without any further ado, let's kick things off. Just want to thank everyone who can make it here today. Excited to talk to you a little bit about Cyvl's technology, how Kimley-Horn is utilizing that technology for their pavement management projects, and a great project we did together for Manchester, New Hampshire. My name's Jeff Greim. I'm the sales manager here at Cyvl. I work with engineering partners all across the country, explaining our services to them and then helping them grow and expand their pavement management and their right-of-way asset mapping divisions within their companies.
Hey everyone, my name is Chris Jacques. I'm a civil engineering consultant with Kimley-Horn and Associates. I specialize in pavement management. I've been with Kimley-Horn for 6 years and practicing pavement management for 8. My goal is to implement and improve pavement management systems in local New Hampshire and Massachusetts communities. I'm a resident of Southern New Hampshire. I did my undergrad at UNH and then I continued on for my master's there and focused in pavements. In recent years, I focused in pavement management for municipalities, but I've got a lot of experience in my career doing these types of assessments for airports. And the reason I mentioned that is because the FAA, they specify a boots on the ground procedure where we're measuring cracks and doing like a true PCI assessment. So I like to bring those experiences and that expertise in the PCI scoring system to these projects. And we'll talk a little bit about that in the presentation. So thanks again for joining the call.
All right. Thank you, Chris. A little bit about Cyvl. We are a Boston-based firm. We've worked with over 300 governments all across the country. We've really seen some unprecedented growth over the last 2 years with the technology that we've developed and its adaptation from engineering firms and municipalities across the nation. We've done over 10,000 miles of roads mapped and managed, and really excited to be talking to you about our solution here today.
All right, and I work for Kimley-Horn and Associates. We're a fairly large firm nationwide. You can see our office locations on the map here. I'd say we're not as well known in the Northeast. We opened the Waltham office about 6 years ago was when I joined, and we're growing, but we're an experienced firm with many offices, many people across the country, and we really do leverage that depth and that reach. We're a full service civil engineering consulting firm, large disciplines of engineering design, development services, transportation planning, and one of those niche services is asset management. So our Waltham office has some of our firm's top experts in pavement and asset management. All right, so to get into the presentation a little bit, we're going to review the data collection process that Cyvl completes and how we leverage that data to help the city make decisions. So first, it's important to understand the concepts of a typical pavement management system, and that's what this cycle here is showing. First, it starts with needing to know, what do I have in the network? So that includes mapping or utilizing the center lines of the roadways, assigning attributes like area, geometry, functional class, establishing how the network is to be segmented, and documenting construction records. So that's all part of like setup and continuous documentation. Once that's situated, we work with our data collection partners like Cyvl to understand the condition of all the roadway segments. This, of course, is an important piece to get right in terms of the quality, the efficiency, and interruption to public traffic. After we have the reliable PCI data, we assist municipalities in figuring out those next 3 questions kind of simultaneously. When do you need to do work? What's the appropriate timing, combined with what work needs to be done at that time and how much is it going to cost? We can establish various funding simulations to explore how the network will perform in different scenarios. And then the last thing to mention is that this is a cycle. It's recommended that you do repeated inspections, say every 3 to 5 years, and revisit your paving plan to make the necessary updates. So I want to expand on that next on the following slide, showing kind of the sequential steps of progressing through a pavement management program. So first, we establish the appropriate network segmentation and the attributes like I explained. Next, we partner with data collection firms like Cyvl to get the reliable condition data. Then as the engineering consultant, we perform sufficient quality control to ensure that the AI has appropriately classified the conditions and that the results are calibrated to any established for that municipality condition rubrics. And then this last line here, steps 4 through 7, that shows other typical downstream processes to get to that report delivery. That includes starting with customization of what treatments are available, what their typical costs are, how effective is the treatment in terms of cost benefit analysis, and how do we forecast the pavements to deteriorate over the next 5, 10, or even more years. This allows us to explore different scenarios. We can simulate if your budgets remain consistent, how would your overall condition worsen, what type of financial backlog rises from that. And another example, if you had extra X amount of dollars, how would your network improve? We can help you discover these answers and present those to boards, councils, your staff departments. Ultimately, we build a multi-year plan that utilizes a prioritization algorithm, but it involves several aspects of engineering, and we'll go over those considerations in a little bit. So onto here, now that we've established the general approach and some concepts of pavement management, we want to expand on those through the lens of the City of Manchester project. So some stats are shown on the next slide. Manchester, as you know, is a large community, has many miles of roadway, over 412 miles. If you could go to the next slide, we can show some stats on it. The cities recognize the importance of establishing a pavement management system to help them make decisions for prioritizing paving needs, improving their network PCI score. This is an established or a mature pavement management system, I would say. It's the third citywide condition assessment that's been done. I believe the first was 2017. Kimley-Horn's been assisting the city with their program over the past 4 or 5 years, including the last 2 collection cycles. Most recent was this one. So there are a lot of miles of road, a lot of needs, a lot of old infrastructure that needs improvement. For this project, the city saw the advantage of leveraging Cyvl's collection system to collect multiple assets simultaneously. So on top of the roadway condition assessment, the city collected inventory data on trees within the right-of-way, manholes and catch basins, signs and their MUTCD codes, and streetlights. So ultimately, we're assisting the city implement a new 5-year paving plan to improve conditions in a systematic way and packaging projects in a logical way. So let's first focus on the data collection aspect, and I'll hand it over to you, Jeff, to talk about that.
Yeah, so this is really, from our talks with our partners, these are their 4 key components that they're looking to solve for themselves. They want to have a one-stop shop for their infrastructure data. Needs to be budget-friendly, easy to implement, fast, high-quality deliverables, and an open standard data easily used by all teams. And I think that last part is really important too. Providing data that can be easily integrated into your current software systems, whatever system that might be, so that you can come up with those, great pavement management and pavement lifecycle curves based on that. Data that you own yourself as well, that we aren't holding up walls against for your access. It's really something that we pride ourselves on as a team, and is something that kind of differentiates us from a lot of those other firms that are on the market today. And really, it's the overall 1, 2, 3 step overview of what we do, how we do it. And I'll get into a little bit more of this as we go on here. Is we map your roadways with a proprietary mobile LiDAR and camera. It goes on the roof of a vehicle. It drives around. It's able then to create these great 3D modelings of the roadway from that data. We have proprietary algorithms that are specifically made to analyze both imagery, mobile LiDAR, and incorporate the GPS components into that data and create these amazing 3D modelings. And from those 3D modelings, we're able to pull out all the different deliverables that you may need for a project, whether that's a pavement evaluation or right-of-way asset mapping and different kind of attributes pulled from those assets as well. And then we provide all that data on easily to use data on our website that can be downloaded, integrated right into whatever kind of software system that our engineering partners might be utilizing. The sensor itself, we make it as simple as possible. It is a mobile LiDAR unit that's highly accurate within about 75 feet, great at creating 3D mobile mapping for your roadways and your right-of-way. We have 360 cameras on that, forward-facing, rear-facing cameras as well. A really high-end GPS unit that can hone in to the exact locations of your assets as well. The ability to do multiple lanes at once, up to 3 lanes, instead of being just 1 lane at a time for pavement assessments, which increases the overall speed of your data collection. And right now, our next model is gonna be able to do up to 55 miles per hour for that data collection as well. To really kind of dig into the data that's collected here too, what really separates Cyvl from a lot of these other firms that are on the marketplace here, it's the fusion of that mobile LiDAR and that imagery data together. Being able to take the key components that you can see from imagery. For instance, when it comes to a pavement evaluation, that'd be all the different types of cracking on the ground. And then really being able to differentiate all the different pavement defects that you can see with mobile LiDAR. Mobile LiDAR is really good at seeing 3-dimensional defects, your bumps, your sags, your rutting, things like that. Those types of defects are almost impossible to see from imagery alone. So the combination of that imagery and mobile LiDAR, they really complement each other nicely. In addition to that, by having 2 separate data sets, allows us to really QA QC our results thoroughly. AI is awesome, AI is great, AI is the future, but AI does make mistakes from time to time. A common mistake you'd come from when you're using just imagery for roadways would be shadows on the road. So shadow on a roadway through an image, that looks a lot sometimes like a utility patch. It sometimes looks like a crack. Because on an image, that's what it looks like. By having that mobile LiDAR component come in as well, the mobile LiDAR is able to correct those kind of mistakes that might have been made by saying, actually, this roadway is actually smooth surface, and we're saying that with a 95% confidence rating. It really allows us to have a thorough QA/QC to have the best overall data quality delivered to our partners that they can then entrust and put their names behind.
All right. So I want to discuss next how we partnered with Cyvl through this process and how the technology is integrated into this here overall workflow. In the Manchester project, we truly did collaborate with Cyvl on getting the condition scores calibrated and improving the AI models to a level that we were completely confident with the PCI scores. The data is utilized in several ways for our analysis and recommendations, and we'll review our process for this, advantages for this level of data here next. So we're looking specifically at that step 3 and what condition is it in. So let's take a look at some of the quality control aspects and some of the things that we're looking at from the perspective of the civil engineering consultant and the pavement expert who needs to deliver that data to the client. So there were several checks and levels of collaboration between our firms to ensure the data was of high quality and calibrated to the existing Manchester data sets. Again, there is a historic evolution of the PCI scores in that system. So when you're making prioritization decisions between almost 6,000 unique segments, we want to be confident in the base condition scores, but also the distress details that were analyzed through the AI. So you can play that video there on the right. You can see an example of just a simple like map-based application that we created and utilized to drive the streets and record comments for the quality control process. So this was all GIS integrated and GPS integrated. So we drove the roads and not every single segment, but a sufficient amount to get a reliable QC results. So on the graphic on the left, you can see some of the things that we were looking for and systematically checked. So first, accuracy of the AI models, as you would think. Cyvl's got a great workflow for appropriate setup of the cameras, collecting at appropriate times of day and weather, flagging if coverage was not sufficient due to parked cars or debris. We explored if the AI algorithms were consistent, accurate, and appropriately calibrate it to the existing data sets. And we also looked at, are the distress types being identified correctly? So the level of detail within the data, it allowed us to complete statistical trend analyses and make the appropriate adjustments more easily. For example, we could filter out if there are high levels of alligator cracking, we want the PCI to be adjusted by X amount, and then we could make that adjustment globally. In a large or even smaller municipal network, you can't do that type of QC high cost and detailed boots on the ground review, like I mentioned earlier for airports, right? So the technology over the past 10 years has greatly improved to allow us to get to PCI scores and other data. So the question is, how close can we get? We want to identify the situations where the PCIs should be brought up slightly or brought down slightly. Our confidence in the data from this allows us to make more detailed or informed decisions downstream. So let's go to the next slide. And I wanted to reflect on the specs or features of the Cyvl data collection process and how they benefited this project, some of the aspects that I appreciated most from their features. So first, the advanced sensor technology. By this, I mean combination of the high resolution imagery, the LiDAR, and the other sensor and equipment systems used to deliver condition data. There are certainly other lower and higher cost approaches in the industry. We saw that this level of technology, though, was appropriate for the municipal setting. It was certainly a good bang for your buck, and I would say for both small and large networks. When I'm working with a data collection vendor, I want to know why a PCI score is scored a 60, for example, and not just a black box of I get all the results or I get that it is a 60. I want to know that there was surface wear detected, extensive transverse cracking, and low amounts of structural cracking. So the level of technology in this project allowed us to complete a more in-depth QC. Not necessarily a longer or more expensive QC, but a more focused QC that is more meaningful. The transparency in the data set, I feel, is essential to a high quality product. Also, with the imagery piece, the 2D and 360 degree, it really is great for the city to have another snapshot in time of their network. It's like having another data point in your Google Street View. Cyvl's camera allows us to see the 2D images, 360 degree views, and essentially you can drive a road in a Street View type interface. Similar to the advantages of the sensor technology and the level of detail that you can obtain, the AI algorithms with machine learning are trained so that we can complete an iterative calibration, leverage my firm's pavement engineering expertise and then calibrate appropriately. So we did that, and it allowed us to implement QC findings globally and monitor the results of the algorithm applied to the whole data set at once. So in the end, this approach led us as pavement engineering experts to have more confidence in the data when moving forward with our analysis and the planning processes.
Yeah, I just want to showcase briefly a mobile LiDAR scan of a roadway in case anyone was unfamiliar with it. As you can see on this picture here, we kind of highlighted a few different defects, depressions, and little shoves as well. These are the type of pavement defects that you're going to miss if you're using an imagery alone solution. And the reasoning behind that is that these are three-dimensional defects. So being able to pull three-dimensional defects from a two-dimensional image is very difficult and nearly impossible in most cases, unless it's a very high severity defect. When you're using a mobile LiDAR solution to complement imagery, you're able to then detect and measure and give severity ratings to these lower level three-dimensional defects that you find within your pavement network. This is an example of like one of the final deliverables that we'd be giving to a client, where we'd be giving the PCI scoring and color-coded scoring for an entire roadway. As you can see on here, it says a 77 score for Kennard Street. But as Chris mentioned earlier, just giving a blanket score is really just a black box. What's really helpful for our engineering firms would be on the next slide. A full incorporated distress detail report, being able to map every single one of your pavement distresses, map them out on these polygons you can see right here on the screen, tell you what type of distress it is, its location, measure its size with the mobile LiDAR, and then give it a severity rating of low, medium, or high. So when we say that a roadway is a 77 PCI score, we add that level of interpretability to it, the why. Well, it's a 77 because you have this much alligator cracking at this much severity levels incorporated with all these other defects. And according to the PCI lookup charts, the score is a 77 because of these defects. And then we're actually able to take the distresses, then overlay them even further onto actual images of your roadways that we are able to collect during the data collection process as well, not just from satellite imagery like you saw beforehand. Now, we didn't do this aspect with Manchester, but we're able then to, once we've created all our 3D modelings of your roadway, we did a number of great things with Manchester, like a sign inventory, manhole covers, things like that. Another great deliverable we do is a pavement marking inventory, being able to say where all your pavement markings are, the symbols that they are, give them a good, fair, poor condition rating as well, and even measure the distances of those line segments as well. So you have a good idea as a municipality, the total square footage of poor or good pavement markings and pavement stripings that you have for your city. So if you were ever to put it out to bid, you now have a much better understanding of the size of the bid you need to have for that. And then again, the mobile LiDAR scannings that we're doing, you can take that those mobile LiDAR files, you can through a 3D modeling software, and we'll be able to produce really high quality 3D models of your township as well.
All right, so back to this graphic, I want to discuss those last 4 steps, step 4 through 7, and answering those questions that you see on the left of cost, timing, and needs. So on the next slide, talk a little bit about treatments. You've probably seen this curve on the right before. It's the typical model of degradation of pavement through its life cycle. X-axis axis showing age, y-axis showing condition deterioration. An important step in the process is to identify candidate treatment types, implement an approach that considers preventive maintenance, and explore the cost effectiveness of each treatment. The graphic here shows examples of this, not necessarily what's implemented at a given time at Manchester, although I'm pretty sure they do have experience with several, if not all, of these treatments. I think all have been done in the city before. Remember, the goal is to apply the right treatments at the right time. So sometimes it's hard to capture that correct timing. You don't want to apply microsurfacing, which you can see there in the picture, when there's excessive structural cracking. You don't want to miss out on the opportunity to provide a treatment just before the pavement deteriorates significantly, kind of at the midpoint or that inflection point of the curve, where if you wait even a year or two, it may require mill and overlay or reclaim, more costly treatments. Our approach was to have a treatment method for each level of the pavement life cycle or condition score, and sometimes these were overlapping PCI ranges between treatments. We then have a cost effectiveness quantitative measure for each of the treatments based on our understanding of the life extension that the treatment grants from city experience and our pavement experience. And then we investigate the typical cost per square yard for each of those treatments and install it in what we call a treatment toolbox for the city. So the next slide, I want to talk a little bit about Drive software. So it's the database for roadway inventory, visualization, and evaluation. As we get into how planning decisions were made, Drive encompasses a lot of the concepts and answers a lot of the questions that we've talked about. This is a web-based software. It was developed and delivered by us, by Kimley-Horn, first implemented 4 years ago for the city of Manchester. It's specific to municipal clients managing roadway networks. The city has utilized Drive and or the prioritization algorithms within Drive to manage their pavement system for the past 4 years. This tool is a one-stop shop to visualize network conditions, statistics, inventory, but it also allows us and our clients to integrate other assets and program projects dynamically over time as that multi-year plan is executed. So you can see a picture of the dashboard here showing some statistics, but I also want to discuss the prioritization schemes that are included in the tool, because that's a big, robust part of its analysis. And those are accessed through other tabs in the software. Our approach is to utilize a cost-benefit metric to develop that prioritization order for each segment and the relevant treatment and relevant timing. That metric we call CBV, cost-benefit value. It includes treatment cost, treatment estimated life extension, consequence of deferral of the treatment, traffic, ADT, or functional class, of course, condition, and then predicted deterioration. So a lot of inputs into that algorithm. It allows us to have a starting point for developing a plan that truly ranks the segments in a quantitative manner. There are many other aspects of Drive that would be great to explore, like being able to develop budget scenarios to defend cost requests. But next, I want to dive a little deeper into the planning piece. So let's go to the next one and talk about the multi-year planning considerations that we implemented in the city. So ultimately, we worked to develop a new 5-year paving plan for City of Manchester under a typical budget level. And we also did one under a higher budget scenario. This was an iterative process because we truly want this plan to be implementable, not just a deliverable from a study. We include city feedback like existing plans or knowledge of upcoming traffic improvements or conflicts with utility company plans. The integration to Drive also allows us to dynamically make changes over time. Say if more budget comes in or a change needs to happen and you need to switch years or postpone a project because of a utility conflict, we have that dynamic integration within Drive. So we first start with the CBV output. Essentially, it ranks all the roads and indicates to us what is the scale of priority across the network. Then there's manual engineering intervention within Drive, and we also use GIS platforms to further develop that plan into a realistic and an actionable one. We want to make sure that we package projects appropriately, look at the proximity of other projects, group neighborhoods, perhaps as it makes sense, distribute amongst wards or regional districts in a reasonable way, avoid gaps or make adjacent segments programmed in the same year. We look to level the budget amongst different years, and we want to have treatments at all levels of the pavement cycle, that treatment distribution. The other thing that we can do, as you can see in the graphic on the bottom, we can overlay sidewalk data, curb ramp data, any other asset data that's geospatial. We can have that enter the equation in terms of manual engineering judgment and overlaying those pieces. And you can see in the bottom there, curb ramp conditions are overlaying the road project plans. So it wasn't an immediate priority when looking at the paving plan, but it is another consideration that we can add into it. So we utilize the visualizations in Drive, in GIS platforms, and tabular spreadsheets to make these decisions and ultimately deliver this plan. And you can see an example of that type of delivery on the right. That's what we provide to the city. So to expand on that, we also work to develop a reliable crack sealing list for the city. By using the distress details from Cyvl's collection, we filtered out structural cracking. We looked at edge cracking, transverse, longitudinal cracks, and we summed it all up and estimated levels of cracking. So in a similar way to the multi-year plan, we explored crack sealing candidates through filters of that crack quantity, PCI scores. We looked at time since the last work or the crack seal, whether that segment was in the 5-year plan or not. And then we had to look at packaging of projects and adjacency to other segments that perhaps have a higher priority for the crack seal list. So we then were able to create reliable crack sealing lists. And when the contractor expedited their schedule and came into town sooner than we expected, we could provide these maps to the contractor, and we were able to more easily prepare this information. So this was a great outcome of the collection data and the analysis. Pass it over to you, Jeff.
Yeah, and just to do a quick overview of all the different deliverables that we did for this Manchester, New Hampshire project. Crazy to think about 33,255 signs that we detected, MUTCD codes for those signs, categories as well. 1.4 million different pavement distresses were detected through our algorithms as well. Over 12,000 streetlights, nearly 10,000 roadside trees, nearly 10,000 manhole covers, and again, nearly 10,000 catch basins as well. It's important to note this is from one pass with our system and able to pull out all these amazing deliverables from that one pass through. Another really great benefit of what we're doing here too is once we have these 3D models created for the city of Manchester, if the city ever wanted to come back, 6 months from now or whenever it may be, and pull additional assets out of those 3D modelings, we're able to do that as well. We don't have to go back and rescan the roadways in order to pull out those assets. Certain assets have longer lifespans than others. Your pavement striping is going to deteriorate over time, but your fire hydrants aren't going anywhere, right? So we have that ability for future project growth across different divisions within the city as well.
So cataloging these assets on top of the roadway assessment made a lot of sense for the city. It allowed the city to collect multiple assets, like Jeff was saying, during the same collection for relatively low cost. So here we have listed a few ways that the city has or intends on utilizing these data sets in the future. First one listed there is something that we haven't systematically implemented at the city, but they've been thinking about how to package multiple assets when project planning and considering the full right of way in prioritization decisions. One example of that is overlaying the sidewalk or curb ramp data that we looked at before onto the road plans and driving the sidewalk expansion plans with the roadway plans. Now that all the assets are identified in a recent collection, also the city can integrate these at the onset of the project rather than react to in-field issues during construction. So there's certainly integration to the project at the development or at the onset. They're able to communicate to utility companies if appropriate, based on if or how many manholes or catch basins or streetlights are within project limits. They can prepare bids with reliable counts for these types of assets. They can quickly navigate to trees within the right of way in the interface and investigate whether action will be needed to be taken that affects road or sidewalk work. So just some examples, again, of how to implement this asset collection into the project. Similar to bid preparation, like I was saying, this data is also helpful for invoice approvals and managing the work order system where they have cataloged IDs for each of these assets. So it's a back check to these collection inventories that have historically been done over time. And then similar to the street view for roads we discussed earlier, it's really valuable to have a snapshot in time of these assets. While the AI has not yet categorized condition for some of these, we can see pictures and an inventory of each asset identified from the inspection. Having that recorded imagery is really a great resource for the city and will be a piece of snapshot in time, like I said before, a history data point that they can reference in the future. So all great potential implementations of these other assets into the overall asset management system. So with that, I'll pass it over to you, Jeff. Any final points before we want to open it up for questions?
No, I think overall it was a fantastic project. We absolutely enjoyed working with you, Chris, on this. You have a wealth of information you're able to provide our team in terms of the QA/QC process, and I think we teamed up very well on this project together.
Awesome.
Yeah,
You too.
from the crowd, maybe we can have any questions about, this project in general, about, Chris and Kimley-Horn's processes when it comes to pavement management, or any questions you might have about our technology and how the two of us could be working together to help your municipality. By all means, open up.
Great presentation. Can you hear me?
Yes, we can. Yeah.
Yeah, I have a quick question about the LiDAR accuracy. I saw that the accuracy is plus minus
Mhm.
1 centimeter, and I was wondering how you calculate rotting in low severity, because there are some requirement that that if it is less than like 12 millimeter, it will be like considered as low severity, and
Mhm.
having this range of accuracy, I'm not sure if it can be pick up accurate. And the other question is that uh, I saw that you collected data in a perspective view, like the distresses are detected in a perspective view from the camera. And the question is that how you convert those into like the area, and you can measure the length.
Mhm.
Is it something that you convert those images, or are you using the LiDAR data for that? I think
Yeah.
that's all my question. Thank you.
Yeah, great question. So that 1 centimeter accuracy rating, that's going to be at the kind of the furthest distance range of the LiDAR from the right of way where we're collecting. The closer it is to the LiDAR, like the distress itself, uh, the more refined that the measurements will be, right? So most of the distresses that we're measuring are going to be right there on the roadway, and that's how we're able to get kind of much more accurate ranges when it comes to those measurements on those distresses for them. Your second question, trying to remember what it went, and it was the how we are displaying our distresses on our imagery. I think what we're doing too is we're fusing together both that mobile LiDAR data with that imagery data. So the different kind of like mobile LiDAR distresses that we're displaying over the imagery is from that fusion process. Now we don't do it, we do that for the overhead view for the satellite imagery, where we're able to take those different distresses that we detected, turn them into polygons and put it on that overhead view. We don't display them though on our front of camera displays that we show on our platform though.
I
Okay.
think I can add to the low severity rutting type of question too, from the perspective of knowing the ASTM well and PCI scores. I would say that the measurement to equate to low severity rutting is not specifically following the ASTM in this approach. It's more identifying the presence of rutting, and that there are lower quantities or higher quantities and relatively low or greater severities. And so it's not a re-implementation of the calculation of the PCI ASTMs, but we have the data to back up what that AI algorithm has been trained on in its machine learning process. So it's not a direct calculation of the PCI, but it has great indicators based on some of the measurements that the sensors took.
Thank you so much.
Thanks. Thanks for the questions.
I think you have the ability to write in the question too if you don't want to unmute yourself.
Yeah, and I think I probably have emailed all of you at this point, but certainly take note of our emails on screen as well. Happy to follow up, talk about pavement management or answer any specific questions.
Okay, I just got a question come in from Cody. It says, for project development, how long does it take to gather and process that data and put together estimated quantities? For example, let's say a 5 mile project. Yeah, so with our system, you can collect, it depends on the area, the size, the type of data collection you're doing, whether it's a city or a county or rural. But on average, a data collector is going to do anywhere between 50 to 60 to 70 centerline miles of unique data collected a day with our system. Um, Typically, our pipeline takes about around 4 weeks of data processing, regardless of project size. If it's a real large project or a couple thousand miles or something like that, may take up to 6 weeks though. But for the majority of our projects, you're talking around at least a 4 week data processing timeline. And then from there, our engineering partners like Chris, they have a lot of work they need to do from that data that is collected in order to come up, with all their different pavement recommendations, and that can obviously vary based on size of project and things like that.
Yeah, it's an interesting question, Cody, and interesting application. I assume you mean project development, so you already have a project in consideration, let's say 5 miles, and you want to collect data. So you're not necessarily concerned about the condition, say, within the 5 miles, but collecting all these other assets and putting together quantities and bids. I would think that'd be it would be a quicker turnaround than like a full network wide prioritization and all the steps that we walked through, because it's more objective in the assets that you're collecting and what your objective is. You have the scope of the project defined and you want to put together these estimated quantities. And so Cyvl could, you know, dispatch teams and collect that data pretty quickly, like Jacques just explained. And we would help, put together.
Yeah, I can just talk. It's probably easier. I was typing just while you guys were talking before, but
Okay.
yeah, the question is more like along the lines of a project level. So I work MassDOT, and
Yeah.
we have our own LiDAR now too as well, and
Yeah.
kind of been interested in using that on a project level. We have UMass doing some different studies with us and whatnot, and we're looking at like asset data extraction and trying to see how we can utilize that information to basically put together a project estimate. Obviously depends on what assets we want, and I think a lot of that stuff's still up in the air at this point. But yeah, that's kind of what I'm looking for.
Yeah, some of the big things that we were able to get in Manchester, the catch basins, manholes, getting those quantities and bids in there. If you don't have center lines or polygons defined for the project area, Jeff, I think you guys can estimate that type of stuff and extract that level of detail as well. So a lot of stuff in the AI system and the collection protocols at the project level. We talked a lot about network level and prioritization, but there certainly is an application for project level development.
Thanks. Yeah, I got one more follow up. I think to that was, have you ever done anything with surfaces? So, for example, like we have some issues with cross slopes and profiles, and there's been concerns in some projects where we may have lost what was originally designed, or it's slightly changed here and there. Have you ever done that using the LiDAR or any of your guys' stuff too?
Cross slope comes up a lot for a deliverable for us to develop it. Our engineering team is confident we can come forward with a cross slope solution. It's kind of on our big board of potential new deliverables for 2025 though. But it's absolutely within the capabilities of the LiDAR that's being collected that we can develop a cross slope kind of deliverable for our end users.
Great. Yeah, and just for sake of conversation too, I guess the one of the reasons I asked that is some of the new equipment. I know TopCon is one of the people that works with like different paving and milling contractors. they can actually program stuff like that, these surfaces into the equipment. So you can cut to certain depths or certain cross slopes and like pre-program it. So it's not just based on sensors in the field and whatnot. Which is kind of interesting. So.
Yeah, the LiDAR technology is really good for that. And I'm sure it could meet the application that you described, the data that would be obtained from the 3D scores. That's interesting application though.
Thanks, guys.
Thanks.
Hi, I hope I'm audible. It's a very good presentation, and I'm very much curious about the data collection part of it. Is there any possibility that the technology could self-render parts of the road in case there are any obstruction while data collection? Or in case it just leaves those spaces blank, how would you fill those gaps?
So, okay, I'm trying to understand. You're asking if it's during the data collection process, if there's any kind of issues with the data collection, like areas of the roadway that doesn't get collected for another reason, how would we kind of correct those?
Yes.
Yeah, okay, great question. Yeah, so the sensor itself is connected via a Wi-Fi network, Bluetooth network to an iPad that's on the inside the vehicle. And as you're driving around, if there's any kind of issues with the data collection, it will speak to the iPad and say, hey, you need to troubleshoot this area. At the end of the day, too, when you're done with your data collection, you'll get a full kind of report of all the quality data that was collected for those roadways, and the roadways will turn from like a yellow to a blue, indicating that good quality data was collected on all those roadways. And if there was a segment that maybe didn't get collected correctly, that segmentation will still show up as an area that needs to be data collected for. We also, before a project is over, before we send the equipment back and everything like that, our team will analyze, do a quick review of all the data that is collected. That way, if we need to send somebody out in the field again to go back to a certain segment to do a recollection, we can accomplish that before the project is completed and the equipment's been sent back and forth and all those things. So we definitely have QA/QC kind of built in place and troubleshooting built in place for those very reasons.
Yeah, we get this question often. Typically, pavement management for network level planning is not intended to get 100% of the surface area. You're trying to get sufficient coverage within a given segment so that you can appropriately say what the condition is. Now, utilizing the technologies, you get a lot more coverage than you would be able to do with a boots on the ground or an ASTM approach. So they have filters and flags for if they didn't get a certain amount of the road. Let's say if they did a fall collection and there's leaves covering a dead end neighborhood, it would flag if they weren't able to appropriately get a condition assessment on that road. So they could do recollection at a more appropriate time, or once parked cars move, or we would dispatch field teams. But I would say for most projects, we don't have to get that because we have sufficient coverage, and we didn't have to do field team revisits for this city of Manchester, for example.
Yeah, and in general, we are detecting about 90% of the defects through our AI on the roadways. To do an accurate PCI score, I believe you only need to detect about 15%. So we are collecting a real large quantity of data in order to get these scorings really at a high accuracy level, well beyond what would be needed for an accurate PCI-based score for a roadway.
Okay, thank you.
Thank you.
This is Owen with Manchester. don't want to put you guys on the spot, and honestly, this is the answer I probably should know. But you had the statistic where you showed all the different additional items that were collected in the city. You know, striping, trees, manhole covers, catch basins. We've been talking about the accuracy of the different collection metrics. I'm curious if you know what the accuracy on those numbers is.
Yeah.
You know, in terms of visible features, is it plus or minus 1%, 0.5%? Do you know that those kinds of numbers?
Yeah, so for our right-of-way asset data collection, we are detecting approximately 95% of those. So if they're like a sign, for instance, we might miss a sign that has, 80% coverage from a tree in front of it, but it's around 95% total of all the assets we are collecting and being able to map it for you. And really, it's pretty on pair with like a boots on the ground survey as well. Even people make mistakes when they're doing a boots on the ground. They might miss certain things as well. But it's pretty highly accurate.
Yeah, I would say the asset identification is pretty objective and accurate. More so with manholes and catch basins and signs. The issue is not really misidentification or categorization. It would be obstacles. And so the numbers that Jeff just gave, I think, would be appropriate. It's a little bit different than a more subjective like condition assessment of roadways. You'd expect a little bit more error in that and identification of these different distress types. There's more QC that would be involved in that and calibration. But for the assets, I think there's certainly a high level of data quality expectation. It's more objective. The machine can be trained really well to know exactly what a stop sign is as compared to X amount of millimeters of rutting. It can identify that stop sign 100% of the time if it can see it.
Excellent. Thank you.
Thanks.
All right, we are kind of running low on time here, guys. So we're supposed to wrap up and by 2 o'clock. I'd say if there is any final questions you'd like to have answered, now would be the time. And if not, you can always email myself or Chris. Our email addresses are right there at the bottom of the screen. So if you got anything else, it's speak up now or email us later, I guess.
Good timing. Thanks for all the questions so far.
Yeah.
Thanks for your time, everybody.
All right. Yeah. Absolutely. Let's wrap it up. Thank you so much for attending. I really appreciate the interactive questions we got at the end there. And yeah, really looking forward to following up with anyone who has any other additional questions that want us to answer for you as well. But thanks again to everyone that attended here today.